Now, as we get to the rational numbers, we see that the notation now, instead of just listing the sets, we can now use set notation to define the sets rather than listing them. So to define the set there, we are saying there that Q, the set of rational numbers, is equal to any value of X, where you see that vertical bar now between the X's is actually saying Q is equal to X. Then the vertical bar is saying where, defining X, where X is equal to A over B. Q is any value of X. Now the set of Q comprises of all the numbers X, where X fulfills this criterion that it's A over B, and A itself and B themselves are both integers, but B is not 0, is not equal to 0. So in other words, any number that can be written in the format of X over Y or A over B, such that A is a whole number, or an integer rather, and B is an integer as well, any integer apart from 0. That's what we refer to as rational numbers. And set notation is defined there. So we see now, let me just go quickly to irrational numbers and then we'll get back and be able to differentiate between the two. Irrational numbers, we're saying, two symbols that are lined on the P. These are any numbers that cannot be written in the form of vulgar fractions, in other words, as X over Y. Such numbers do exist. Examples include the square root of 2. Actually, many square roots are written in that particular way. Defining irrational numbers in set notation is a bit more complex if we're now going to use specific members. So it's easier to just say the set P is all real numbers, the set R, minus rational numbers, the set Q. So anything that is not in Q but is in R is what defines P. That's what we mean when we're writing it in set notation. Now, getting back to that, let me quickly just try to illustrate the difference between rational and irrational numbers. Irrational numbers are any numbers which cannot be written in the form of an integer over another integer, and that's sort of vulgar fraction. What this means is if you are to divide one number into the other, and you will get a remainder, and you continue dividing that remainder, and continue dividing that remainder, gives you another remainder, and you continue dividing it up until a point where there is no remainder, regardless of how many iterations you went, regardless of how many decimal points you have gone into. But if you get to a point where there's absolutely no remainder, where the last number is 0, that number is said to be a rational number. It can be written in the form of X over Y, because you've been able to successfully divide Y into X. And it did have a remainder point something, but at some point it ended up terminating. So if you take that very long number and multiply it by Y, you will go back and get X. That is your rational number. That is why we see that rational numbers can even now be written as 0.25. It doesn't necessarily have to be in the form of X over Y all the time. It just basically means that whatever number is there can be represented. If you want to represent it in the form of X over Y, it is possible. You can have 0.25 represented as 1 over 4. You can have 47% represented as 47 over 100. You can have 5 represented as 5 over 1. So they all have that ability to be represented as X over Y. However, if you were to take a number and divide it by another, you divide Y into X and it gives you a remainder, and you continue dividing, and you continue getting remainders forever. You get to a point, you never get to a point where there stops being remainders. You're constantly getting remainders. So you end up having an endless number of decimal points. That is what we refer to as an irrational number. Because now whatever value you take, you're going to stop somewhere. And if you decide to stop there, and you multiply that number by y, the answer that you'll get will not be x. It will be slightly less than x. It will be something slightly less than x. Right, an example, if for instance now, let's say you divide 10 by 3, you're going to get 3.333333 whatever. So whatever that number is, if you multiply that number, that 3.33333 whatever, by the number that you had divided by, which is y, which is 3, your answer is not going to be 10, it's not going to be x. It's going to instead be 9.9999999 whatever. So that is why we say that is an irrational number. However, let me just point out here that if the pattern is recurring, like 3.3333, that number there is just always going to be 3, a recurring pattern. What can be done is you can represent that number with a little bar on top of the recurring sequence. In this case, just 3.3 or 33, and then you put a little bar on top of the 3, the last 3 there, to show that this is continuously going to recur. Numbers which are written like that, even though they are irrational, you actually now are finding a way of trying to rationalize them. You can actually claim them to be irrational if you put that little bar. If you're dividing a number and then the recurring number at the end maybe is 1246, 1246, 1246, that pattern that's constantly repeating, you just put a bar on top of it, of the entire pattern, if it's 4 numbers. Yes. That way you're now making the irrational number rational. That's how you rationalize an irrational number. But that's neither here nor there. Let's move on to the next set, real numbers with an R. Real, these are all the numbers that we know, really. Remember, we said there are imaginary numbers, but these are numbers that don't really exist in real life. These are imaginary. So all the numbers that you know, all the numbers that occur on the number line are real numbers. Whether they're integers, fractions, they are negative or they're positive, or even 0 itself is a real number. So we represent that by saying R, or the set R, is equal to X. X is any value of X such that negative infinity is less than X, which itself is less than positive infinity. In other words, X is greater than negative infinity, but is less than positive infinity. In other words, it's greater than the smallest number that would exist and is larger than the largest number that would exist if such a number did exist. Okay, and then finally, then we move on out of the real numbers, we get into the imaginary numbers, where we are saying imaginary numbers are based on the imaginary unit I. So there's a constant, the value I. So that constant, that value I, is given the value that if you square I, the square of I is equal to negative 1. I squared is equal to negative 1. So in other words, I is the square root of negative 1. Such a number cannot exist, because when you multiply a negative number by itself, the answer is always going to be positive. When you multiply a positive number by itself, the answer is also always going to be positive. So there's no way that you can actually multiply a negative number, or you can actually multiply any number by itself and get a negative in real life. Let me just put it that way. So imaginary numbers don't exist in our real universe. but we use them. These numbers are used by mathematicians, they're used in engineering, and sometimes some applications there, here and there in computing require that you actually create a number that doesn't really exist. Imaginary numbers. And then finally we have complex numbers, which we said complex numbers are numbers such that which are made up of a plus b times I, where a and b are real numbers and then I is an imaginary number. I is an imaginary number. So a real number plus the product of b and I, another real number, and I. So in other words, complex number is a sum of an imaginary number plus a real number. That's what a complex number is. Now, what we said at the beginning, I'm just going to repeat this again to say the reason why we have complex real numbers being a subset of complex numbers is because we can set the value of b there to 0. So then you have a plus 0I. So a is a real number plus 0, which is a real number, times the imaginary number. So 0 times any number eliminates that number. So you end up with your number being just a. That's why we have a situation where a, real numbers alone, are part of the set of complex numbers. Like this video and subscribe to this channel for more such content.